slope on topographic maps. What can we do with it? If you have a sloping rock formation that you can actually identify from a topographic map or a sloping outcrop, is there anything you can use to extrapolate data, to measure and to calculate the actual slope? Well, this is what we will do in the next few minutes, going through that exercise. Now, a gradient is, of course, a slope or a degree angle that works along there. Let's take this map and see what we can find as far as gradients are concerned. Where is the steepest part of the map you can see? Now, little hint, the steeper a slope is going to be, the closer my contour lines are going to be spaced. So I think this area right here looks pretty steep. It has one of the closest spaced contour lines in the whole map. Well, where is the gentlest part on the map? Or the one with the least amount of slope? Well, several places that could qualify. I see one right there toward the west or the northwest, but I think there's one in the upper right-hand corner of the map that even qualifies better. Right, this space. Contour lines are extremely far apart, which means that slope must be gentle. But how gentle? What is actually the degrees of slope that we could extrapolate from that map? Well, a little trigonometry might help. Let's picture a triangle. You can see that I placed the distance base just between some contour lines. That makes the measurement easy. The height, of course, we can get from the contour interval. On the distance we can measure from the bar scale. Alright, we need lengths in feet, the height in feet, and a calculator to figure out the degree of slope. For measuring the length using the map scale should be easy. However, there's a problem. While the elevation on this map are given definitely in feet, the scale, the distance scale, is only in meters and miles. Hence, we probably will have to convert. But let's give it a shot anyway. We're taking the scale, or a copy of it, and place it right below our arrow here. That should give us a distance to this point. Alright, let's read it. I'm coming up with 770 meters on the meter scale or thereabouts, and my miles are about 0.48. Alright, but we need to convert. Now here's a little side note. When doing conversions in science, it is best to use some process that is called dimensional analysis or factor labeling. This way you will never make a mistake. I can ask you a quick question. Well, would you divide 770 meters by 3.28 feet, or would you multiply 770 meters by 3.28 feet? Well, some of you may guess, but let's find a surefire way that you can use so we'll never make a mistake. Here's the deal. The first rule is don't think. Don't think how you're going to do the conversion, but always start a conversion like this. Write down your number, a multiplication sign, and a line. Really, the number times line. This is it. Then you can start thinking. Which unit would you like to get rid of? Of course, we don't want meters, and we put this in the bottom of the fraction. We would like to end up with feet. That goes on top. You can see we haven't written down any number yet, but this will help us not to make a mistake. Okay, the conversion is given. 1 meter equals 3.28 feet. Let's cancel out the meters. They will go away. We are left with feet, exactly the unit we want. Let's put the 1 where the meter is and the 3.28 go with the feet. Okay, now you can see that we multiply 770 times 3.28 gives me 2,526 feet. That worked rather slick. Let's try this again with the miles. Again, write down 0.48 miles times line. We would like to get rid of miles, we'd like to end up with feet. Let's cancel out the miles and plug in the number. The miles, of course, the 1 goes with the miles and the 5,280 go with the feet. Again, 0.48 times 5,280 gives me 2,534 feet. Well, there is a discrepancy. Which is the better number? Believe it or not, it doesn't really matter. Round to significant digits. In 770, we have only 2 significant digits, so we have only 2 significant digits in 0.48 miles. Hence, both the numbers 2,526 and 2,534 need to be rounded to 2 significant digits, which is the exact same number of 2,500 feet. That is our distance we're going to use for our calculation. Now, what about the height? Well, the height we can get from contours. I count 1, 2, 3, 4 steps, 4 contour lines that we have to climb over, which is at a contour interval of 40 feet, 4 times 40, 160 feet of elevation gain over a distance of 2,500 feet. So we have a rise over run. Sounds like trigonometry. The angle theta can now be calculated from the arctangent of the ratio between the vertical and the horizontal, or rise over run. Well, let's unlimber the calculator. Where is the arctangent located on your calculator? Several models have several ways of accessing the arctangent function. It may be a shift key that gets you to the tangent raised to the -1 power. A 10H can be found on some calculators, or the inverse button with the tangent function can be used to get the arctangent. Before you get too much into the calculation, do me a favor. Push in the number 1. That would be, for example, 100 feet over 100 feet, or a 45-degree angle. Now see if your calculator gives you 45 degrees if you take an arctangent of the number 1. If it doesn't, then your calculator is set to radians instead of degrees, and you would need to go to the mode, the setup mode, to switch this one to degrees, so you will get the correct answers. However, in our calculations here, the arctangent of the ratio of 160 feet over 2,500 feet will give you a very small angle of 3.6 degrees, which is true to our 2 significant digits. 2 significant digits in 160 and 2 significant digits to 2,500. A very, very gentle angle. Now let's try this again with the steepest part. As you can see at the steepest part, right by the picnic area, my contour lines toward the bottom start to space out. I would like to get really the angle of the steepest part, which is between 2 of the index contours. So I can draw a very small triangle in there. As you can see, I have a short distance to travel with quite a significant elevation gain. Now let's find out how we're going to do this. What's the height? Well, the height is between 2 index contour lines. My contour interval we already figured is 40 feet. How many contours would I have to cross to get to the point uphill at the end of my, or corner of my triangle? Well, it's 10 times 40 or 400 feet, which would be exact the distance between its 2 index contours with 200 feet each. Alright, what about the distance? Well, we're going to use a trusted old ruler again. I know we have to convert, but I trust that you can do the conversion yourself by now. So let's give it a measurement. I just will stick with the meters, about 140 meters. Alright, 140 meters converted into feet. You should be able to do this now. 459.2 feet. Well, is this the number we're going to use or write down? Well, not really. Let's round this one to significant digits. in my 140 meters, the ones I measured, they are 2 significant digits. So again, I need to round 459.2 to 2 significant digits, which comes out to be 460 feet. Alright then, what is my angle on the steepest part? Arctangent of the ratio of 400 foot elevation divided by 460 foot of distance, which gives me a steep angle of 41 degrees, almost 45 degrees, which is of course much steeper than the angle we have calculated in the gentle part. I hope this will be useful now for you to calculate slopes when necessary, so you can get an idea how steeply certain features are located on the map.